Deep in our oceans lurk a series of mysterious, invisible global ocean currents that possess the power to alter life on Earth as we know it. They're intrinsically linked, working together like giant conveyor belts to pump oxygen, life, heat, salt, nutrients seamlessly and efficiently around our blue planet. They are the unsung heroes in regulating global climate. The systems that so often take a backseat in the climate conversation. That is, until something goes wrong. Perhaps the most influential of these ocean current systems is the AMOC, the Atlantic Meridional Overturning Circulation, a keystone of Earth's climate system, and a system scientists have warned isn't just slowing down, but could actually collapse as early as 2025. While this has happened before, it hasn't happened for nearly 10,000 years. And there's one big difference this time. We're here. How can something so life-altering have snuck under the radar without us knowing? If the worst were to happen, what would happen to life on Earth? I'm James Stewart, and you're watching Astrum Earth. Join me in this video as we find out what's going on below the surface. Okay, so that's pretty intense, isn't it? This is the year. We're in 2025, but considering the AMOC collapse is what inspired the 2004 film The Day After Tomorrow, it doesn't feel like that is just around the corner, does it? There doesn't seem to be much coverage or even urgency on this subject. Indeed, a lot of people won't have ever heard of the AMOC. Perhaps that's one of the big problems with a force you can't see or measure. Because the truth is, there have been indications that the AMOC has been slowing down for the last 60 or 70 years, as our planet has warmed. And some scientists have gone a step further, suggesting the AMOC has declined by at least 15% since 1950, and is in its weakest state in more than a millennium. The big clue? A big cold blob that's appeared over the northern Atlantic. Bizarrely, this region is the only place in the world that has cooled in the past 20 years or so, while everywhere else on the planet has warmed. Any guesses as to why that might be? Yeah, it's the AMOC slowing down. One of the AMOC's main jobs is to shift heat around. It's one of our planet's largest heat transport systems. It's moving the equivalent of 50 times the amount of energy humanity uses. The same amount of energy that flows through 1 million power stations all at once. So when it slows down, this region gets colder. Since 2021, the general thinking in the Intergovernmental Panel on Climate Change, the IPCC, was that the probability of crossing the tipping point for a collapse this century was less than 10%, with medium confidence. But as recently as October 2024, 44 climate scientists from 15 countries sent an open letter to the Nordic Council of Ministers, suggesting the risk of the AMOC collapsing has so far been greatly underestimated and is higher than previously thought. A new study published in Nature Communications used sea surface temperature data stretching back to 1870 as a way of assessing the change in strength of AMOC currents over time, ultimately estimating it could collapse between 2025 and 2095. So which paper is correct? I decided it was about time we found the answers. So let's dive into the AMOC, what it is, how it works, previous ice ages, how it's evolved, what happens if it collapses, and perhaps most importantly, when or if it will collapse. I suppose a good place to start when you're trying to work out why something isn't working is to understand what it is in the first place. What does this mysterious invisible beast that could bring down life as we know it actually do? It's easy to forget that we are all connected by one enormous interconnected body of water, and the AMOC helps make sure our oceans remain as one, like a sort of giant mixing bowl. It moves water, heat, nutrients, dissolved gases, and microscopic life around Earth through ocean currents. The AMOC is a brilliantly complicated system of those ocean currents and eddies, which are circular currents of water. It forms a glorious, giant vertical loop that spans the entire length of the Atlantic Ocean, and it would look like a giant piece of spaghetti just draped across the map. And it's those currents which are pretty interesting here, because there's a few different types of them. Tidal currents occur close to shore and are influenced by the sun and the moon. Surface currents, which are influenced by the wind, and much slower currents that occur from the surface to the sea floor. They're driven by changes in the saltiness and ocean temperature. Those last ones are the one we're most interested in here. This process is called thermohaline circulation. Thermo meaning temperature and haline meaning saltiness. The AMOC is part of this thermohaline circulation conveyor belt, circulating water from north to south and back again, in a long cycle within the Atlantic Ocean. It drives warm water northwards along the ocean's surface and cold, deep waters back southwards. In doing this, it delivers heat and nutrients to the colder latitudes and also transfers carbon to the ocean depths. Things begin off the east coast of North America, where the Gulf Stream, which is part of the AMOC, carries warm water from the Florida Straits up to the Grand Banks off Newfoundland. Now from there, the North Atlantic current then travels across the ocean towards Europe and the Norwegian Sea. When this warmer water reaches the subpolar regions nearer Greenland or Arctica, not only does it cool down as it loses heat to the atmosphere, but it also becomes more dense. The cooling forms sea ice, and as the ice forms, salt is left behind in the ocean water. Now that large amount of salt makes the water much denser, causing it to sink down into the ocean at a depth of 2,000 to 3,000 meters, where it's then carried back southwards. That's where the overturning in AMOC comes from. This sensation creates a vertical overturning circulation throughout the ocean basin, as the water is eventually pulled back up towards the surface and warms up, thus completing the cycle, much like your central heating system works at home. Every second it moves an incredible 17 million cubic meters of water northwards, equivalent to around 7,000 Olympic-sized swimming pools. This in turn moves 1.2 petawatts worth of heat, 100 times bigger than all the global energy produced on Earth from all power sources. And all of that is critical in regulating global climate around the world. As impressive as all of that is, and it really is, it all happens rather slowly, which is quite surprising for such an awesome system. In fact, the AMOC's entire circulation cycle is slow. It takes an estimated 1,000 years for a parcel, any given cubic meter of water, to complete its journey along the belt, and it really can't afford to get any slower. But sadly, that's where the problem lies, because it does seem to be slowing down. But why? Before we press on, quick terminology tidy up for the AMOC and the Gulf Stream, as the two are often confused. As we've just touched on, the Gulf Stream is a part of the AMOC system, not the system itself. It's like an internal organ the AMOC couldn't function without. The Gulf Stream originates at the tip of Florida. It's a warm and swift Atlantic Ocean current that follows the eastern coastline of the US and Canada before crossing the Atlantic Ocean towards Europe. Its job is to ensure that the climate of Western Europe is much warmer than it would be otherwise. For example, where I am today, it's about the same distance from the equator as the cold regions of Canada. Yet here in England, we enjoy a much warmer climate. If it weren't for the warm water of the Gulf Stream, England would have a much colder climate. Perhaps not full day after tomorrow vibes, but the UK would be at least 3 to 4 degrees Celsius cooler, and in mainland Europe things would be colder still, by at least 10 degrees Celsius. It's like a really fast highway, part of the journey taken by the warm water through the AMOC, as it travels from the South Atlantic to the far north. When that highway ends, the warm water takes a different, smaller route, continuing its journey northwards. As it moves through the Atlantic, it loses heat through evaporation. This leaves behind cooler, saltier water, which eventually hits the fresher waters of the North Atlantic. The Gulf Stream is caused by a large system of circular currents and powerful winds, called an oceanic gyre. There are 5 oceanic gyres on Earth: the North Atlantic Gyre, South Atlantic Gyre, the North Pacific Gyre, the South Pacific Gyre, and the Indian Ocean Gyre. Given its location on Earth, the Gulf Stream is part of the North Atlantic Gyre. Now we've cleared up our currents, let's focus back in on the AMOC, and more specifically, the impact climate change is having and has had on it. As we touched on at the start, everything on Earth is connected, and the same is true here. From that big clue we talked about earlier, the big cold blob that's the only place on Earth in the last 20 years to have cooled, well, that's not just a surface cooling. That cooling extends down to a depth of 2,000 meters, and is sort of the smoking gun to a slowing AMOC. You see, as well as that area getting colder, its salinity is also declining. It's actually at its lowest levels since measurements began 120 years ago. Because of this, the water is an awful lot less dense. And that's really significant, because it's becoming much harder for that water to sink down and join up with the deep, colder currents we talked about before. One of the main reasons scientists think this could be is there's lots more fresh water now melting off ice into our oceans due to an increase in greenhouse gas emissions. At least 2 studies analysing state-of-the-art climate models and observations have shown that the recent North Atlantic warming hull is of anthropogenic origin and is caused by reduced northward oceanic heat transport related to greenhouse gas emissions. One of the main reasons we're able to attribute some blame towards humans, as alluded to there, is by looking back to the past. To understand conditions before regular temperature measurements began, we must turn to proxy data, the traces of past climate change left behind in slowly accumulating archives, things like ice sheets or seafloor sediments. Proxies like the ratio of oxygen isotopes found in the microscopic skeletons that make up much of the deep floor sediment provide a record of past surface water temperatures. The size of sediment grains on the ocean floor reveal current speeds above it and allow us to reconstruct past sea surface temperatures and other parameters. What they suggest is a long-term weakening of the AMOC since the early or even mid-20th century. Climate models have long predicted its decline in response to global warming, and the physics behind these predictions is understood. In addition, the paleoclimatic data also strongly points to human activities as the cause, in that AMOC weakening coincides with a period of unprecedented modern global warming. In short, it's very likely that humans have significantly increased the conditions in which the AMOC is prone to being unstable. We can observe several changes here. There's a rise in greenhouse gas emissions and Arctic amplification. There's also an increasingly enhanced water cycle, intensified by more energy from the sun, which creates more extreme weather like floods and droughts. There's also more evaporation in the subtropics and more precipitation in the high latitudes. Now, these things are all happening before we've even mentioned melting sea ice. And here comes the big one. The Greenland ice sheet is melting at a rate of around 270 billion tonnes per year, and this is what makes the water less and less salty. The fresh water dilutes the salty water, and this is salt advection feedback, a positive feedback mechanism that affects the strength of the AMOC, as the major tipping point that ultimately leads to a slowdown or even collapse of the AMOC. In 1961, US oceanographer Henry Stummel recognised how the Atlantic water salinity leads to an AMOC tipping point. In other words, the AMOC flows because the Northern Atlantic is salty, and it's salty because the AMOC flows. It's chicken and egg, or in more technical terms, a self-sustaining feedback effect, which works the other way around as well. If the Northern Atlantic becomes less salty because of an inflow of fresh water, the water becomes less dense and the AMOC slows down. It brings less salt to the region, which then slows down the AMOC further. One of the most interesting things in this crazy cycle of ocean systems and currents is that the AMOC has a bit of a track record of being less than stable. In other words, it's collapsed before. And its collapse has historically been linked to some pretty extreme climate events. I sometimes forget that we're still in an ice age, albeit an interglacial one, but the climate during the last glacial period was also far from stable. To give us a clue into past AMOC behaviour, we can examine some dramatic climate changes that have happened in the recent past. Recent, that is, from a paleoclimate perspective, so the last 100,000 years or so. Now, one thing we know from studying the paleoclimate is that some of the most abrupt and striking temperature changes, which are known as Dansgaard-Oeschger events or DO events, they're periods of abrupt warming followed by a period of slow cooling that occurred during the last ice age. They were likely caused by instability in the AMOC. This graph shows temperature reconstructions from ocean sediments and Greenland ice over the last 60,000 years. The green line here refers to sediment data, and the blue line refers to ice core data. What's interesting is as the blue and green lines drop dramatically throughout the time period, they coincide with Heinrich events, marked red, and DO events, which are numbered. This demonstrates an unstable AMOC in all likelihood led to these dramatic spikes. During the Younger Dryas period, which was a period of extreme climate change, the AMOC slowed abruptly around 12,500 years ago. This caused a period of near glacial temperatures in the northern hemisphere. This was caused by the melting of the Laurentide ice sheet, which resulted in several mass iceberg surges into the North Atlantic Ocean. They're known as Heinrich events. At certain times, these ice sheets release large amounts of fresh water into the North Atlantic. We can see recorded evidence of these events in North Atlantic marine sediments as layers with a large amount of coarse-grained sediments derived from land. These layers, which are continuous across large areas of the North Atlantic, are evidence for both an increase in icebergs discharged from the Laurentide ice sheet in North America and a southward extension of cold polar waters. Scientists have hypothesized that these freshwater dumps reduced ocean salinity enough to slow deep water formation and therefore the AMOC. Since the thermohaline circulation plays an important role in transporting heat northward, a slowdown would cause the North Atlantic to cool. Later, as the addition of freshwater decreased, ocean salinity and deep water formation increased and climate conditions recovered. Okay, so hopefully by now you've got the general gist of this pretty large, very real problem. So we turn to the big question of when is it going to collapse? Note my use of when here. The thing that struck me the most while recording this video is that there are so many different papers written on the AMOC, and they all have different answers to that question of when. But the one thing they all seem to agree on is that if we continue on our current trajectory, it's no longer a question of if, but indeed when this collapse occurs. As we stated at the start of the video, until a few years ago, the general thinking in the IPCC was the probability of crossing that tipping point this century was less than 10%. In the latest 6th IPCC report, they found that even for a low emissions scenario, the AMOC would weaken between 4 and 46% by the end of the century. But there are now conflicting reports suggesting that a collapse could happen as early as 2025. So which year is it? What's going on? Who's right? Who's wrong? It's a great question, and I wish it was as straightforward as that, I really do. So much of this comes down to how the AMOC is being modelled and the factors and physics taken into account to do that. A big hole in all of these models actually is that beyond paleoclimate data, we haven't really been measuring this stuff for long enough to give us properly accurate data. The IPCC reports use a model called CMIP-6. That consists of the runs from around 100 distinct climate models being produced across 49 different modelling groups. Critics have noted that the AMOC model they used for this system was a too stable AMOC. When they input the AMOC to the model, they had to tune it, as you would do a car. And the critics' suggestion is that this was a little too well tuned and didn't represent a realistic scenario of estimates for an AMOC collapse, hence churning out these rather conservative estimates. For many critics, however, it goes beyond just being a conservative estimate. It actually becomes a significant underestimate. On the other side of the fence, we've got papers saying it's going to collapse between 2025 and 2095, which is where we got that 2025 number from. But how did they get those numbers? These scientists use a different type of modelling called reanalysis, where they look to move past the limitations of our short observational record, relying instead on sea surface temperatures in the North Atlantic. It's important to note here that sea surface temperature as a measure of AMOC collapse is currently widely debated in the scientific community. The actual observations of the AMOC since 2004 have long since discredited the evidence that the authors of this paper are actually using. The 5 data points they show were collected several years apart by ship surveys, and it's well known and well established that they give a highly misleading impression of AMOC decline. To be fair, the authors acknowledge this in the discussion, and they do say there's large uncertainty in their conclusions. To bring us back then to the big question of when will the AMOC collapse, that paper we just mentioned using sea surface temperature as a key measurer concludes that there's a critical mean of the year 2057, a date supported in another paper which offers an estimated collapse between 2037 and 2064 with a mean probability of 2050. I'll let you make your own mind up on a specific date for AMOC collapse, but reading all that, one thing seems for sure. If we keep going the way we are with global warming, something pretty intense is going to happen in many of our lifetimes. A full AMOC collapse would be a planetary scale disaster. There's no getting away from that. But if this thing collapses, well, what happens to us? It's not looking good in Europe. Let's start there. European cities would experience a 3 to 10 degrees Celsius drop in temperatures in just a few decades. Some areas will be much worse. February months in Norway, for example, could become 35 degrees colder every century. It's not like you'd have a new ice age in just 2 weeks, but the Northern Atlantic region and Europe in particular will cool substantially. England, Wales, Scotland and Ireland would look more like northern Canada. There'd be a huge increase in winter storms right across Europe, and significantly less precipitation in Western Europe. This has a huge knock-on effect to things like agriculture in places like France or even in Great Britain. It'd be a bit like trying to grow potatoes in northern Norway. It just wouldn't work. However, Europe is not the only region to be affected. The sea level in the Atlantic Ocean could rise as much as 70 centimetres, submerging many coastal cities around the world. There would be densely populated places on Earth right now where people simply could not live. Scientists also predict a shift of the tropical rainfall belt to the south. This is bad news because the rains move away from the rainforest and go to regions that are not used to so much rainfall. This would mean droughts in some regions and floods in others. Rainfall in the Amazon rainforest would undergo a drastic change. There'd also be less rain in the Sahel and a weakening of the summer monsoon in Asia. As the northern hemisphere cools, the southern hemisphere will become increasingly warmer. The heat from the Pacific Ocean will not be transported to the North Atlantic, and instead, it ends up staying in the tropics, causing dramatic temperature increases there. It will also reduce the carbon uptake of the ocean, because the AMOC sinking in the Northern Atlantic takes a lot of carbon down into the ocean depths, where it's safely locked away from the atmosphere, and the last thing we need right now is more carbon in our atmosphere. Despite all that we've talked about, there are some people who might suggest actually parts of the world cooling might not be such a bad thing. Considering all we hear about is the Earth getting warmer, maybe an AMOC collapse might counteract that. The truth is, there is nowhere I can think of that would be better off. In fact, it's the opposite. If it were just a case of averages, then somewhere like Germany might see a balance just because of where it's positioned. But weather is not a climate average, it's seasonal and highly variable. Within the average, you can get warm air from the south or cold polar air outbreaks from the north. These contrasts will just be more pronounced if Scandinavia and Britain cool, while Spain and Italy warm, for example. This will drive much greater variability in the weather, and that's bad for agriculture. It causes more storms, there'd be more major extreme weather events, the kind we haven't seen before. You get the idea. Continuing this trail of thought, some scientists have suggested an AMOC collapse may temporarily delay some of the issues the Amazon is currently facing, if coupled with the effects of global warming. In the initial phases of an AMOC slowdown, so greater rainfall and lower temperatures in the Amazon, that could partially offset temperature-driven stresses that the rainforest vegetation experiences. This could delay the potential for the Amazon to transition into a savanna-like state. It's important to note this would only be a temporary amount of time and also depends on the relative timing between an AMOC collapse and global warming. If global warming worsens past a particular threshold before an AMOC collapse, the rainforest could irreversibly enter a savanna-like state. Due to these fluctuations in the AMOC, the Amazon could shift its seasons, with the dry season becoming the wet and vice versa, a change that would severely impact the overall system. The AMOC is clearly something we need to watch incredibly closely. But how do we actually do that? How do we keep track of changes in the AMOC to monitor how quickly or how far the slowing down is progressing? Scientists measure the AMOC using scientific instruments deployed in different latitudes across the North and South Atlantic Oceans. The National Oceanography Centre, the NOC, is the UK lead of 2 international programmes in the North Atlantic, Rapid Climate Change and UK Overturning in the Subpolar North Atlantic. Both programmes deploy sensors attached to wires that are hundreds to thousands of metres deep. They're known in oceanography as moorings. These instruments have special sensors attached to them, which measure things like ocean current speed, temperature, salinity, and direction of the water crossing the arrays. One of the major things to keep an eye on in relation to when this collapse might be imminent, the sort of alarm clock, if you will, is the flow of water in the Atlantic, which has been measured with the RAPID project since 2004. The other measurements help us monitor water mixing during winter in the North Atlantic and Nordic seas. If the deep mixing starts to decline a lot, that could be an early indicator that we are approaching a tipping point. Now, whilst there are some signs of this, as we've shown throughout this video, we don't have enough data yet to be sure when that might be. Last big final question. We know the AMOC has collapsed before, and it's come back again. So could it not just do that again if it collapses? Well, sort of, maybe. Let's say it did collapse. Even if that freshwater input into the oceans from ice melting decreases to current levels, the AMOC may still remain in a collapsed state. The ability of the system to not return to the initial state once the forcing is reversed is referred to as hysteresis. Interestingly, the UK's Met Office models show that there may be a temporary resilience period in the AMOC after a threshold has been crossed, during which the AMOC could still recover if the freshwater input is reversed rapidly. In one Met Office model they used, the AMOC recovers if freshwater inflow ceases after 20 years, but not if it ceases after 50 years. This gives a 20 to 50 year temporary resilience, but the temporary resilience period would be lower if fresh water was added at a higher rate. The last time it collapsed, it took 1,000 years to recover, though the past is not a direct analogue because there is also massive CO2 forcing this time. CO2 is already higher than at any time in the last 15 million years, and we are still in an ice age after all. As we come to the end of the video and I think about all that we've discussed and all that I've read to get here, it's very hard to get away from the fact that if we continue going the way we are, there is likely to be a significant slowing down or even collapse of the AMOC in many of our lifetimes. But when's it going to happen? I think we can say 2025 is almost certainly ruled out because of the data points we discussed being too unreliable. On the other end of the scale, the IPCC's estimate around the end of the century, to me, feels too optimistic. But the decade that does seem to come up more reliably than any other is something around the 2050s. The answer to stopping this is as obvious as you might have expected, and an answer you probably already knew. We must significantly slow down the rate at which our planet is warming. It's so simple and so obvious, and yet sometimes it can feel like such a huge undertaking. Often when we think of climate change, we think of the things we can experience or we can see. The droughts, the extreme weather, the temperatures, the floods, the melting sea ice. But rarely do we think about what we can't see, the underlying causes. Forces just like the AMOC that go under the radar, yet have the ability to severely alter life on Earth. And it always finds a way to bounce back and to respond. And it would do so again if or when the AMOC collapses. Whilst a collapsing AMOC is not new news geologically, we've never had such an advanced, populous civilization living on Earth when it's happened before. So yeah, planet Earth will survive this event. Whether humanity would, or at the very least billions of people's current ways of lives would, is a more serious question. The AMOC demonstrates just how intricate and delicate the systems that govern Earth are, and it's as mesmerising and awe-inspiring as it is deadly and dangerous. Like so much on planet Earth, the AMOC joins the very long list of things we urgently need to take care of, and in my view, it has to be near or even at the top of that list. Astromurf is all about making our incredible planet accessible and relevant to you. We want to show you a side to it that maybe you haven't seen before. To do this channel will leave no stone unturned in terms of the data, the research, and the analysis you'd expect. But it'll combine that evidence-based investigation with excellent storytelling and, most importantly, an audio-visual experience you remember. Thanks for watching, and we'll see you in the next one.